Loading effects on the frequency of oscillation. So in this case, you may have your original frequency as 1 or 2 pi square root of LCT, and that's commonly as C. And then you may have another thing, which is the quality factor. And the quality factor will be Q squared all over Q squared plus what? 1. That is the loading effect. And that is the formula for it. So let us solve a very simple problem that will determine what we're doing. Okay?
Yes, sir.
Example. Determine the frequency for the oscillation in figure 24.4. That is the figure we're considering. I will still give you the values. Okay?
Yes, sir.
Assume there is negligible loading on the feedback circuits. I think you know the feedback circuit here on the board. You know it now?
Yes.
That is C1, C2, and the inductor, right?
Yes, sir.
And that is Q is greater than 10. So now, B, find the frequency if the oscillator is loaded to a point where the Q drops to 8. First of all, we look at the data that's required in solving this problem. We look at the data that's required in solving this problem. One, we can say the inductor is 50 millihertz. 50 millihertz, not megahertz. And then the capacitors, we may decide to say 0.1 microfarads or 0.01. So commonly, let us use 0.01. 0.01 microfarads, 0.01 microfarads. The diagram remains the same, please. Okay? So when you have that, what you are expected to do here is this. Let us say data in a normal way that we solve calculations. You may say C1 equals to C2 equals to what? 0.01 microfarads. You say L, which is what? 50 millihenries, which is equals to 50 times 10 raised to minus 3 henries. Right?
Yes,
Top. So if you are expected to calculate the total capacitance, here you can see that the capacitors are connected in series. This C1, C2. And mind you, capacitors connected in series are calculated as resistors connected in parallel. You understand? So CT equals to 1 over equals to 1 over C1 plus 1 over C2. You can do it this way. So if you feel you want to change this, then you make this one the standard formula C1, C2, and that will give you 1 over CT equals to C1 plus C2 all over C1, C2. This will hold for this side, okay? Yes. Then when you cross multiply this, you have C1, C2 equals to C1 plus C2 bracket CT. Making CT the side, you have CT equals to C1, C2 by C1 plus C2. That gives you the formula for calculating the total capacitance of this network here. And this will be 0.01 microfarads and then 0.01 microfarads by 0.01 microfarads plus 0.01 microfarads. And when you check, scientifically, you are going to have your solution as 0.0091 microfarads. The solution will be 0.009 microfarads. Yes. Because of lack of time, I would have solved it, but that's the way to be. So if you want to calculate the resonance frequency of the circuit, then the resonance frequency FR equals to 1 over 2 pi square root LCT. That is the total capacitance we have calculated here. FR will be 1 over 2 pi square root What is the inductance? 50 millihenry dot times what? 50 millihenry, or let me put it in brackets. So I have 0.0091 microfarads, right?
Yes, sir.
In brackets. So this will give FR equals to 1 over 2 times 3.142 square root 50 times 10 raised to minus 3 henries, 3 times 0.0091 times 10 raised to minus 6. And if you do it and do it religiously, you are going to have a solution that will be 7.46 kilohertz. 7.46 kilohertz. This is the frequency. This will be the resonant frequency of the circuit that we're discussing. Okay?
Yes, sir.
Then, if we are trying to look at the loading effect of the circuit, we are trying to consider the loading effect of the circuit. What will be the solution? The 3, that is the third one. The loading effect of the circuit, you are going to have the resonant frequency as what? 1 over 2 pi square root LCT, and then square root of Q squared all over Q squared plus 1. Already the resonant frequency has been calculated here for you, right? Which is what? 7.46. FR equals to 7.46 kilohertz in bracket. Then here, what you are going to do, you are going to use the 8. Q is what? 8. That is the attenuation, right? So that is 8 squared all over 8 squared plus 1. Then when you do that, faithfully you are going to have LR equals to bracket 7.46 kilohertz. And this will give you 64 divided by 65. What is this? What will be? I think 0.9 something. I think I did that. I got it was 0.992 to 0.9923. You have then you are going to have FR equals to 7.46 kilohertz by 0.9923. I think it's not 0.0. 0.9923. When you do it very well, finally you are going to have a resolution of 7.40 kilohertz. Yes. 7.40 kilo. That will be the solution, right?
Yes.
We have another one called the Hartley oscillator. Called what? Hartley oscillator. Hartley oscillator behaves same as the cockpit. The only difference between the Hartley and the cockpit is that there is an interchange of values. There is what? An interchange of values. You have 2 inductors and a capacitor. Instead of having 2 capacitors and an inductor, you have 2 capacitors and an inductor, right? Yeah. Here we'll come down to this circuit here. And this will just give us our Hartley oscillator straight away. Here, we're going to make justice with this circuit by saying this is a capacitor now. And this will be an inductor connected with another inductor. This will be L1, L2, and then C. Are you there? This is Hartley. Hartley usually have 2 inductors and a capacitor. So if the value of N1 equals to L2, you are still going to have the same formula. This same formula that we had in the other one. Are you getting me? But in this case, the C will be independent, but the L will be in total. That is C, L, T. Are you getting me? Yes. Instead of the C to be T, is the inductance. When inductors are connected in series, it's an addition. This inductors connected in series. So the answer is LT equals L1 plus L2. Inductors connected in series. This is the formula. This is the answer you're going to have. So you can just use this one as LT. If you want to calculate the resonant frequency in this case, you can just say this is C, bring this other one down, and then say this is LTC. You are good to go. This is the tanker circuit. You can determine your resonant frequency from here. And the answer you are going to have is going to be, you use the same method we used in determining the commutative selector, but you are going to have this. 1 over 2 pi square root of C L what T. Instead of CT, you see independent because it was a inductor that we taught at, not the capacitors. Does it make sense?
Yes.
Good. That's what will happen. So even if you have a similar problem to solve, it will still give you the same thing. The only difference here is that you are going to have the attenuation. The attenuation for the circuit, the attenuation is L1 by L2. The attenuation B equals to L1 by L2. Are you there? L1 by L2. Okay. So that is all we need to know about this circuit. The 555 timer, which is the last one we're going to discuss based on the localization of oscillators, we'll now look at how we can get the on time and the off time, especially when you are designing something, whereby you see some people designing something and they'll tell you, oh, and this thing, the way it's working. In fact, I designed an extension system recently with a student, and I used the 5-5 timer, where you see the lightings, the green, the red, and the green and the blue balls alternating. It was a 5-5 timer I used in actualizing that circuit for the 5-5 timer. In fact, there are some things that when you design these days and you don't put the fancies on them, people don't even value them. Even if you design an extension that is so good, they will not value it as when they see something, a fancy thing being attached to it. But it's obvious when it's always say, I like this extension. Look at how the lights are flip-flopping or assembling or running. I said, yes, that's how we do it these days. But it was just an attachment, essentially that was attached. But the major components that I used a ballast, I used an NTSC, a negative temperature coefficient component, to compensate for voltage losses and suppressions. So with this, people are beginning to admire, but I know within me that is just for fancy, and it will help people. Or if you have a child that loves watching these kind of things, you know, there's some children that like that kind of thing. When they see, they will go and sit in one place and be looking at it. Instead of them to be disturbing, they allow the parents to concentrate. I mean?
Yes.
No, it's what I experimented in the school. My colleagues in the department and student electrical, you people saw it, I mean?
Yes.
You have seen it now, live.
Yes.
I tested it, you have seen it.
Yes.
And some other students from other departments came in, they saw it. Me, I don't have any restriction for any student. Whether you are from license, lab check, or anything, you have an issue with the course. And it's something I have an idea of. You can dash and ask me, do you understand these particularly physics areas? Which I have a very vast understanding. I can still help you out. You are here to understand, you are not here to be confused.
Yes.
So if you have a challenge, as we're here, you feel free. You have a problem, just come over to me. If it's something I can resolve, if I can't do it, I can refer it to somebody that knows it better than me. One, I didn't know what physics as a core course. I did it based on the secondary school experience, but with the knowledge of electronics, I think that I can go further, deeper. I've gone further and deeper in it than this. So I expect physics students to be here, because there are some things that I'm sharing here that are not just common, which somehow they may not even hear it from their own department, because their level at this time has not gone up to. But IJB sometimes surprises people. You see them asking after questions. You see it, and you start sweating. It happens like that here. So the 5-5 timer as an oscillator, a 5-5 timer is a relaxation oscillator. It is used everywhere. You can use the 5-5 timer to on and off a switch. You can time a switch. You can say after 15 minutes, come on. After 10 minutes, go off. You can do it.
Yes.
Provided you know the calculation. What is the on time? What is the off time? Then the total time. That is what we consider in 5-5 timers. One, you need to calculate the duty cycle that is required. And that will enable you to do the right design. Okay?
Yes.
The one we're discussing here The 5-5 timer is a versatile integrated circuit with many applications. So much, you cannot even mention all. So many applications. Even as I'm finishing, if I finish the lecture today, maybe later in the day you see me at the voltage divider. You see the kind of components that the 5-5 timer is having. It has what? 2 comparators. Measure it, say it. It has 2 comparators. It has 2 comparators. That is, these are op amps. The one that will send the upper limit and the lower limit of the supply that's coming in. The other one is the flip-flop, which is a logic circuit that can determine the on and off time. A discharge transistor. A transistor that can finally discharge when you switch off, and then a resistive voltage divider. These are embedded in the small IC of 8 terminals. If you see the big diagram of that something, you'll be surprised. Look at it. If I raise it up, these are the 2 op amps. This is the flip-flop. This is the discharge transistor now. You understand? So the lower and upper comparators are here. You can see them. Now, when you look at this very internal structure of the op amp, you can see resistors connected to the network. The resistors are there to see that this supply, it operates from 0 to 15 volts maximum. From 0 to 15 volts. So any supply that is more than that, you see it will be heavy. 5-5 timers are very sensitive, but they are very good to play with, just like op amp. If I play with them, you will like them. You can modify and do anything with them. They are so good to play with in electronics. Especially when you feel to economize, let's say you go and buy 5 transistors. A single 5-5 timer can carry out those functions for you conveniently instead of cascading circuits. There are some designs that I use a single IC to execute, which if I go on transistor, I have to cascade out with 3 transistors to get that power. But so there are some ICs that I just get one and it will just give me what I need, and I don't even need to solve again. So as you can see, the 5-5 timer is a very versatile electronic component that is to be used. It is a 2-stage device whose output can be either a high voltage level or a low voltage level because of the 2 comparators. The low level comparator and the high level comparator. The state of the output can be changed with proper input signals. It is determined by the amount of inputs that is being fed in. Just like when you have logic gates. Anybody that have heard of logic gates here? Computer students, have they treated logic gates with you?
Yes. Yes.
So what happens to 9 gates before they deliver an output? AND gate. Let me not go to NAND. AND gate. All the input, what any of the input is high is OR gate.
Okay.
And then when all the inputs are high, AND gate can deliver and give you an output. And the NOT or the inverter, when one is high, if it's high, it will give you a low output. That's how they behave. Okay? We'll have that many. We'll have exclusive or exclusive no, we'll have low gate, one NAND gate, there are many. So they behave like that. It's not only these components that we have. How many components that we can deal with in electronics? But today we're looking at the 555 timer. Okay?
Yes, sir.
In a physical diagram, the pin 6 and pin 2 are connected together. Let me draw the diagram for you to see. One thing about 555 timers is that they are very good at using terminal 1 as the ground. Terminal 1 is always the ground. Okay?
Yes.
Terminal 2. Terminal 2. 2. Terminal 6. Terminal 7. And then this terminal 7 is the discharge. Discharge DCH here. And this one is a threshold. Threshold. And this is the trigger. Terminal 2 is a trigger. And the output is usually on terminal 3. Output is usually what? On terminal 3. This is out. And then terminal 4, terminal 5 is also connected to a decoupling capacitor and then to the ground. It's not too necessary, but it's very important. And then we'll have terminal 4 here as the reset pin. 4 as the reset. And then terminal 8 as the VCC. So terminal 8 and 4 and 8 are connected together and connected to the general supply that is coming into the circuit. And this is taken from there with a resistor connected between here and the discharge. And another resistor is also connected here. Of a whole, if you are connecting this in unstable mode, then you have to bridge terminal 6 and 2. And then this will finally go to ground again. And then this capacitor C1, C2, R1, R1, 2. Now, there is something that we need to know about this very circuit very well. This is the control, okay? That is the diagram of a 5-5 timer on the board, okay? Connected to operate this 5-5 timer is connected to operate in the unstable mode or as a free running realization oscillator. When you say unstable mode, that is just as if you are lifting your hand up, the other one is coming down. You understand? That is the unstable free running. That is this one on, this one off, this one on, this one off. Are you getting me? Yes. That is free running. That's what we call free running. This other one on, the other one. That's how it works. Notice that the threshold is now connected to the trigger. Threshold pin is connected to the trigger. This is the threshold that is connected to the trigger. The trigger is that point in which an external source comes in to make the 5-5 timer to work. There are connections that you can do that. There are designs that you can do that. But if you don't need it, you have to grab it. You need to what? Connect it together with the other one. The external components R1 and R2 form the timing circuit. The timing circuit of this very component, 5-5 timer, is only determined by the value of R1, R2, and C1. And for reasons whereby you feel you want to be adjusting the duty cycle or the timing of the system, you can connect a variable resistor here. If you can easily time it the way you want. You connect a variable resistor. You know what I mean by variable resistor? Huh? Few students believe in potentiometer. When they see something like potentiometer, they can easily understand we have 1 terminal, 2 terminals, 3 terminals with a spindle up here. Huh? Something like a volume of a radio. Huh?
Yes.
You understand what I mean?
Yes.
So if you want to connect it, you short the middle terminal with another one and connect like a resistor. Here you can vary a resistance from 0 to 10K. If you connect it here, you can vary it. So you can make the timer to be, the switching to be very high. Or you can lower the switching of the bulbs. You can make one to stay for like 5 seconds, go off, then another one, 5 seconds, will come on, like that. And there are times that when you adjust it to be very fast, you can't even notice when it's switching on and switching off, depending on the position of that variable resistor or preset resistor that is on the board. So now, The capacitor that is connected on the control terminal, which is terminal 5. Terminal 5 is strictly for decoupling and has no effect on the operation. Is to limit any AC component that's attempting to enter the timer. I think I made mention of decoupling when the resistor and capacitor were connected in the Hartley oscillator.
Yes.
Huh?
Yes.
So decoupling is very important though. When you design and you see that maybe you're noticing that there will be a noise effect, you can just put it somewhere. Say, please stay here for me, there's any nonsense. Stop it. Abi?
Yes.
Initially, when the 5-5 timer is turned on, the capacitor C2 is uncharged, and thus the trigger voltage at pin 2 is at 0. When initially you turn on the 5-5 timer, we're giving a supply of 9 volts. 9 volts DC here. What will happen is that this capacitor initially will be uncharged, and the trigger pin will not notice anything. But after some time, the capacitor will begin to charge. How does it charge? Graph where capacitor charging is like this. When it reaches a threshold, it begins to. This charging and discharging, charging and discharging. One thing I want you to know is that when a capacitor starts to charge, it will be charging based on the amount of supply that is given to it. If 9 volts is given to a capacitor, the capacitor will charge to that voltage and keep it. And do what? Keep it. And be operating like that. Until when the supply is removed. The voltage between the terminals and the capacitor, which is stored in the dielectric, and the capacitor is not gone, is still there. That is why if you visit a maintenance shop and you see a technician working on a television and he mistakenly put off the TV from the source and touches a capacitor, you see a very heavy shock. The reason is because the capacitor you are using, which is about 150 microfarads, 400 or 400 or 450 volts or 650 volts, has discharged into you. And that is why they use something like a bulb connected to the capacitor. The bulb will come on and then discharge. When the bulb comes on, that is the full charge. The voltage in that capacitor was at the peak. After some time, the bulb will go off, telling you that the capacitor is discharged. So those of you that are very good at seeing electronic circuit boards are touching them. One day you have a story to tell. Yes. So this capacitor, when the circuit is powered, the capacitor will at first, in fact, it will not be working. It will not be charging. It will wait until after some time it will begin to charge. That is when the resistor R1 and R2 will begin to give the timings that is required. When it charges to that level, this causes the output of the lower comparator to be high and the output of the upper comparator to be low, forcing the output of the flip-flop and thus the base of QD. How low and keeping the transistor off. At this time, the transistor that is there is off. It's not functioning because it's waiting for the something to charge. Are you getting me? Yes. When the capacitor C1 begins to charge through R1 and R2, as shown in the diagram, when this capacitor begins to charge through R1 and R2, look at what happens. Through R1 and R2, what will happen is that the capacitor voltage will reach up to 1/3 VCC. It has two rates. 1/3 VCC is the lower level and 2/3 VCC is the upper level. Now, by the time the capacitor charges to this level, something happens. 1/3 by 9 is what? 3 volts. Abi? Then 2/3 is what? 6. Can you see the level of, can you see it now? Yes. So, the lower comparator switches to its low output state when the capacitor voltage reaches 2/3 VCC. The upper comparator switches to its high output state. You reset the flip-flop causing the base of QD to be high. The capacitor, the transistor at that time switches on. That is the time to switch on. When the voltage reaches to a level that all the comparators are on now, the transistor that's inside, which is QD or Q, will now switch on, and then the time the operation will start. And that's the time you see if you connect a diode here, maybe you connect a light emitting diode here. Do you know what will happen? Maybe 1K. Or some people prefer to use 330 ohms. So just say green color. Then it will be given an output. When you put a meter here, an analog meter, you see the pointer will be moving on, off, on. It will go high, come back to zero, telling you that there's a pulse signal. And the signal that will come here will be like this. It's not sinusoidal wave. This is how 1 0 0 1 0 1. 1 is on, 0 is off. Okay? Are you getting me?
Yes, sir.
Off is 0, 1 is on. That is how the bulb will be like coming on. So when you see people designing things like this, then you know that they are using 5-5 timers. They are using 5-5 watt timers. This sequence creates a discharge path for the capacitor through R2 and the transistor as indicated. The capacitor now begins to discharge. At a point, when you switch off, the capacitor will begin to discharge. What happens? Causing the upper comparator to go low at the point where the capacitor discharges down to 2 or 3 volts. That is 6 volts of it. The lower comparator switches high, setting the flip-flop which makes the base on QD low and turns on the transistor. At that point, when the discharge begins, the system is tend to be finally switched over by the capacitor C1 being discharged. I told you that the capacitor C2 is only for decoupling. It does not have any major operation in the circuit. The result is a rectangular wave output whose duty, or square wave output, whose duty depends on R1 and R2. I initially told you that the timing and everything that's happening there depends on the value of R1 and R2. So if you want to get the timing, the C is also another big factor that you need to consider. So if we want to get equations for the high and the low, well, we'll soon finish, don't worry. We're soon finishing very soon. By selecting R1 and R2, the duty cycle of the R2 can be adjusted. Since the capacitor C2 discharges through R1 plus R2 and discharges only R2, duty cycle approaching a minimum of 50% can be achieved if R2 is smaller than negligible as R1, so that the discharging and discharging times are approximately equal. A formula to calculate the duty cycle is developed as follows. There's a way we develop the formula for calculating the duty cycle, which I'm going to draw it on the board. We'll now look at it appropriately, okay?
Yes.
Good. The time that the output is high, TH is how long it takes C to charge from 1 or 3 volts to 2 or 3 volts. And it is expressed as the on time or charging time of capacitor C2, no, C1, of capacitor C1 is solely dependent on, that is, when you say the on time, that is the T high. That is the high time. Are you getting me?
Yes, sir.
And then, or you can regard the charging time of the capacitor C1 is from 1/3 volts, 3 VCC to 2/3 VCC is dependent of this formula TH or T on. Are you getting me? 0.649 R1 plus R2 bracket C. I told you that the charging affects what? That's C1, right? Because that's C1. Affects is done by the presence of R1 and R2 and C. Because the capacitor charges and energizes the resistors at that point. It charges from 1/3 VCC to 2/3. That's the time the system begins to come or comes on. Okay? Yes, the time that the output is low, that is the T low or the T off, when for the off time or discharging time of the capacitor regarded as TL equals to 0.649 bracket R2 by C1. Do you know why we're using in the discharging time 694 now, sorry. It's 694, it's not 69, 694. 694. 694. 694. Now, the discharging time I first only C2. It says only R2. It first only resistor R2. But the charging time affects R1 and R2. Am I communicating?
Yes, sir.
So when that happens, what you are expected to do is this. What will be the total period of time that is required? That is the sum of TH and TL. So we can say T equals to TH plus TL. Agreed?
Yes. Yes.
These markers are really soft for me. And TH. This will give you 0.694 R1 plus R2. So C1 and C2 are the same. Let us be using C, right? C1 plus 0.694 bracket R2 over what? C1. Because you're adding it now. Are you not adding it?
Yes.
That is, you're adding equation 1 and equation 2 into equation 3. So when you have that, what would be the next thing to do? And what would be the resultant effect? The resultant effect of this is that you will need to remove the like terms that are there, which you may tend to have. Huh? C1s what? Uh-huh. C1s and this, right?
Yes.
0.694 C1. No, shouldn't be plus now. R1 plus R2 plus R2. Is it not?
Yes.
So this will give us 2R2. That is 0.694 C1 R1 plus 2R2. And that is T. That is the total time that is required for that to happen. So what do? Finally, the percentage duty cycle is what? It's calculated by the duty cycle of, and you know that your T is what? Huh? Your T is what? So your T is TH, right? So this equals to TH by TH plus TL, right? 100%. Now, what is going to be the TH now? The TH is going to be 0.694 bracket R1 plus R2 C1 all over 0.694 bracket R1 plus 2R2 bracket C1. And this will help us to delete the cell faithfully, right?
Yes.
And you have R1 plus R2 over R1 plus 2R2. This is another way of determining the duty cycle of the circuit. And if you do that, whereby you want to get a 50% duty cycle, then R1 must be greater than, far greater than R2. Or R2 must be far less than R1. Or you can say, when R1, no, that should be R1. Well, R1 is far than R2, then we are going to have a relationship that looks like this. It will be R2 all over R1 plus R2. In percentage, Abi?
Yes.
In percentage. Let us be putting our percentages very much.
Yes.
So that God will give us some. We're expecting a percentage. So, finally, we have come to the conclusion of today's lecture on oscillators. And I believe you people have shared a very great experience.
God explaining the circuit about and much about the capacitor.
Which one?
The C capacitor.
C1?
Yes, C1. So you say it always store a very high current on the voltage. So and
The maximum value is 10 microfarads.
Yes, and
16
it takes
volts
time
or
when the system is off before it will discharge. So supposing you want the capacitor to be discharged, immediately the system is off. What will you do?
No, we don't discharge capacitors like that. If you're not careful, you can even damage the circuit. Yes, a working circuit, don't ever try to discharge a capacitor like that. You can only discharge a capacitor when you're working on a circuit that you have a short problem. Problem was short. Are you getting what I'm saying? But for you to make such a very gross mistake of looking at a working circuit and discharging a capacitor, it will create a problem that you cannot even start. You only discharge on the circuit that you are repairing. What? Don't try to. You can only do that on a board that you are working, not a board that is working already. Yes, because the transient current will flow easily to other components and damage them. Do you know why lightning disturbs the electronics in the house? Huh?
No, sir.
Yes. Because some electronic systems are manufactured and not properly shielded against such effects. So when there's a lightning effect, and you know that the components in your system, some of them are active, and this thing normally happens when there's a heavy lightning and your building is not properly grounded. A television that you use overnight and switch off, the following day you discover that take it to the mechanic and tell you that everything is born. Yes. Because some buildings are not properly grounded. You do the installation work, when you finish, you say, there's no money, just go. It's like that, I think there's light, now you bought the gym, there's light now. Never came and there's light, just go, don't worry. All you know is that you have cheated the technician, let him go. Because if you come to dig a earthing and put this to put the earth roll, definitely you will request for money. So let him just go. But you have cheated yourself, not the person. Yes.
So I have a question aside this topic.
Yes.
My question is that.
No, wait. You have a question, but let us try to give a summary of what you have studied. I think it's better that way, first. Any question on what I've said or the lecture that I've just delivered? Huh? Huh? Yes, I'm listening.
My question is that, like we find oscillators in our regulators,
No. It is on system that are frequency dependent. You can find the status.